तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
In the last class, we saw that the inverter formulated using MOSFET or junction FET has a characteristic as shown. This is the transfer characteristic. We saw that initially the transistor is off when Vi is starting from 0. Okay. Until Vi reaches Vt, the no current will be flowing through this, and therefore this will be at VDD. Thereafter, this is an important point, thereafter the current starts flowing because Vi has exceeded Vt. Okay. So the current starts flowing. The question is, in which region this is working? Obviously, when the current starts flowing, the potential here is going to be very nearly VDD. So VDS is very nearly equal to VDD, and Vi has just started making this FET go into conduction, and therefore this FET is in the current saturation region. Primarily in the characteristic curve, you will see that this is the current saturation region. When Vi is just equal to Vt, the point at which current saturation region is reached is Vds equal to Vi minus Vt itself, which itself is very nearly 0. That means at the origin itself, okay, this would have gone to current saturation region. That means when the low current is there, even when there is a very low voltage Vds, okay, it would have reached the current saturation region. So this is in the current, this is important. So first it starts off with current saturation region, okay, and therefore the equation to be satisfied is that Ids is equal to k times Vgs minus Vt whole squared is valid, and using that information we could get the slope of this characteristic as minus Gm into Rd, where Gm was equal to 2k into Vgs minus Vt, Vgs being Vgsq, the quiescent voltage here, okay, which is Vgsq or Viq. Okay. So that slope corresponds to Gm into Rd, it is negative, indicating inversion. That is the small signal gain of the amplifier. This is the common source amplifier, and this Gm keeps changing as you go further and further. Right. As the current is lower, the Gm is going to be lower, okay, because Gm is really 2k into Vgs minus Vt, and current is k into Vgs minus Vt whole squared. So as current is lower, Gm is going to be lower. Same thing happens in the case of a bipolar junction transistor. As current is increased, Gm is increased. Okay. So this, at this particular point, when V0 or Vds becomes equal to Vi, which is Vgs minus Vt, that is the line separating this current saturation region from triode region. The transistor enters the triode region, the equation to be used is IDS is equal to 2k into Vi minus Vt into V naught minus V naught squared by 2. Okay? That is for IDS, and this relationship is followed. So, basically we are using the equation V naught is equal to Vi that is V naught is equal to Vdd minus IDS into. So, this is the equation that is plotted there. IDS being taken as different depending upon the region. Here it is 0, here it is 2k into Vgs minus Vt whole square or Vi minus Vt whole square. Here it is k into Vi minus Vt whole square. Here it is 2k into Vi minus Vt into V naught minus V naught squared by 2. All these things we had done in the last class. Now, therefore, for small signal, and we have also now understood what is meant by small signal. It causes second harmonic distortion, and in order to keep the second harmonic distortion low at a particular value percentage compared to the fundamental, we have to use this small signal approximation, and therefore, in the small signal region the equivalent circuit this is what we had included. Equivalent circuit is going to be this is gate, the source is grounded, this is gate, and to this we are applying, let us say, your small signal delta Vi, and current is defined. What is GM? GM is defined as delta IDS by delta VGS at a particular value of VGS Q. Okay, this is the definition of GM. Okay. So, if I want the current here, delta VGS is same as delta Vi, change in Vi, okay, because VGS is same as Vi in this case, right. So, if there is a change in delta VGS because of change in delta Vi, then we have this current as Gm into delta Vi, because Gm into delta VGS, which is delta Vi, is delta IDS, the change in output current by definition. So, this is a very simple equivalent circuit, a current source which is inducing a current which is Gm times delta Vi, that is occurring at the drain. So, you can see that this is identical to the bipolar equivalent circuit between base and emitter. If the voltage was VBE, the current source current was Gm into delta VBE, which is delta Vi, exactly same. Okay. Gate being replaced by base, okay, source by emitter, drain by collector, if you want the bipolar. Right. So, as far as the equivalent circuit, the only thing is at this point it was very nearly a short circuit, okay, because current controlled, it was a forward biased junction, whereas here it is an open circuit. Now, there is a difference between base and emitter. Even though it was a forward biased junction, we had negligible base current if alpha were exactly equal to 1. Okay. So, this current was very nearly 0 even in the case of base, which really means that if you take an ideal transistor with beta infinity or alpha equal to 1, even this impedance would have been infinity. Right. But in practice it is not infinity, it is of the order of few kilo ohms, okay? Whereas in the case of field effect transistor it is of the order of tens of mega ohms. Okay, so you can keep it as open circuit. At this point, once again just like the case of a transistor, we have here the channel resistance not being infinity, not an ideal current source, characteristic is not exactly horizontal, there is a small increase that we have explained in terms of lambda, if you remember, right. In the equation the current IDS was given as K into VGS minus VT whole squared into 1 plus lambda times VDS. So it was dependent upon VDS, it was not all that independent. The saturation current, the so called saturation current was not really remaining constant, it was increasing with respect to VDS, and this lambda factor we brought in, right. That is therefore responsible to result in what? An RDS. So what is RDS? By definition, RDS is defined as delta VDS by delta IDS in the what? Current saturation region. Ideally speaking, this should be infinity, whereas now how much is that going to be equal to? This is going to be only depends, so this is lambda times, okay, K times VGS minus VT whole square, okay. That is 1 over that. Delta IDS by delta VDS is lambda times this, okay. So delta VDS by delta IDS is 1 over lambda into K into VGS minus VT whole square. So strictly speaking, K into VGS minus VT whole squared is really the current, quiescent current of the transistor, okay, because you are going to evaluate it at a particular operating point. So we will put this as VGS Q. So K into VGS Q minus VT whole squared is really speaking IDS Q. So you can therefore obtain this as 1 over lambda times IDS Q. So this lambda should be given by the manufacturer, okay, or you have to make some arrangement to measure it, okay. This also is an important factor associated with the field effect transistor. What is the order of impedance that it results in? It will be of the order of hundreds of kilo ohms, okay, this RDS. Unlike in the case of common emitter transistor, which is of the order of few mega ohms up to 10 mega ohms, this here is going to be of the order of hundreds of kilo ohms. So this particular thing is to be normally taken into account in the equivalent circuit, and the composite equivalent circuit now using all these non-idealities is simply this. So using this information we can now connect RD, because this RD is connected to ground AC wise. So RD comes into picture. So the gain of this amplifier, which is delta V naught by delta Vi, is equal to, what is delta V naught? This is the voltage here across RD. So delta V naught by delta Vi is going to be minus, why minus? Because this current is going to increase as Vi increases. So, you are putting it this way. Therefore, this potential will be plus and this will be minus. So, what is marked as delta V naught is going to be really negative times Gm into RDS parallel RD. This is the effective gain. If it is infinity, we get back what we have earlier assumed, which is Gm into Rd. If RDS is infinity. Otherwise, if it is finite, it is Gm into Rd parallel RDS, RDS by Rd plus RDS. This is going to be the voltage gain of a common source amplifier, biased to work at voltage of VGS Q. What is the input impedance? Input impedance Ri is going to be infinity here, right. This is normally the case with this field effect transistor. It is infinity here between gate and source, and output impedance seen from here. Always output is, you remove the so called load, and then look at the output. In this case is how much? Nothing but RDS. So, we know now the basic stage parameters: input impedance, output impedance, and the gain. So, once again I have to tell you that all the analysis that we have adopted for bipolar junction transistor, common emitter amplifier, is also valid here. It's exactly similar. Once we know how to bias these things, etc., the analysis in terms of replacing it by an equivalent circuit is exactly similar. Only these symbols are named differently. That's all. The parameter, for example, Gm remains Jm as Gm. This, instead of calling it as Gs, we'll be calling it as base emitter. Instead of this being infinity here, there will be some resistance RBE here. And this is RDS is replaced by RCE here, right? Collector to emitter. That's all. So, it is the similarity that is important, because the same analysis is adopted for all the circuits, whether they use field effect transistor or bipolar junction transistor. Now, we will just see how, therefore, the biasing arrangement also is similar to that of bipolar junction transistor. We will just therefore see the similarity between this and bipolar junction transistor. I have to bias this at a certain voltage called VGSQ, otherwise it is not possible to operate this. So, if I want to use it as an amplifier, I have to put here a voltage of how much? VGSQ. Then everything is all right. That I could do, but I don't want to get a separate voltage. I already have VDD applied here. So, I would like to generate this VGSQ from VDD. What did we do in the case of a bipolar junction transistor? We put R1 and R2 and attenuated this. So, we can do that. So, we get this Thevenin's voltage, which is the same voltage as Vg, which is equal to VDD into R1 by R1 plus R2. This was the same in the case of bipolar junction transistor. We did the same thing. What we said was, it is not only generating a Thevenin's voltage, but it has a series resistance, okay, Thevenin's resistance, which was equal to R1 parallel R2, which is in this case is going to be called as RG, right. Earlier, right, it was RBB we had called it, right, RB we had called, and this was VBP, right, to Thevenin's voltage. So, this therefore is equivalent to VDD, then RD, ground, then we have RG and VG. As given by this. This is pretty convenient because there is no gate current, and therefore, it does not make any difference what the value of RG is. The gate voltage is going to remain same as VG. This is the advantage of the field effect transistor input as compared to the bipolar junction transistor. In the case of BJT, we had this trouble that there was current flowing through this RB, and we had to make that current, okay, or we had to make that voltage drop across this resistance very small in order to make it become negligible compared to VB. Right. So, this we had to do in the case of bipolar, whereas here it is. On the other hand, while applying a signal using a coupling capacitor, it had to be now coupled by capacitor because this is at a DC potential. I want to add the AC without disturbing the DC. So, I will now couple this by means of a capacitor CC1. This we had used in the case of bipolar junction transistor also. So, when I do this, this particular thing definitely takes away current, signal current, because as far as the FET is concerned, it is not taking away any current. It is this down that takes some amount of signal power. Okay. So, RG has to be made very large. RG has to be made very large in order to make it take away as little amount of signal power as possible. Okay. So, this RG is made pretty high in the case of field effect transistor, of the order of, let us say, few hundreds of kilo ohms you can make, because actual impedance of the field effect transistor is of the order of what? It is an open circuit, right? It is a field oxide. So, it is of the order of 10 to power 12 ohms or so, okay, almost nearly. So, you can put even resistances of the order of mega ohms if they are available readily, no problem. Okay. So, this impedance is not going to get affected at all, right. It is this impedance which will dominate. So, in the gate of a MOSFET, you can put resistances of the order of mega ohms if they are readily available. In the gate of a field effect transistor, since it is a junction and junction resistance is of the order of tens of mega ohms, you better put resistance of the order of hundreds of kilo ohms. Okay. So, this kind of design we have to remember here in obtaining the voltage VGSQ that you would like to have. Now, in the earlier situation we said we wanted an operating point. Now, this is an operating point which is fixed without any problem, okay, fixed. But are you happy with it? I am not very happy, because if I change the field effect transistor which is having a different value of K, the IDS is going to change, because the IDSQ is equal to K times VGSQ minus VT. So, IDSQ still depends upon this equation. It depends upon K, it depends upon VT. So, if I change the FET, the operating point will be different for the same value of VGSQ. So, this will cause problems. Why? Because the operating point here is important in terms of what VDSQ it is having. VDSQ is equal to how much? VDD minus IDSQ into RD. This is the VDSQ. If IDSQ changes, this VDSQ changes. If VDSQ changes, I am not sure, right, when the signal comes, whether this VDSQ is sufficient to maintain it in the current saturation region. So, this is an important thing. For a given value of RD, this VDSQ depends upon IDSQ, right. Higher the IDSQ, lower will be the VDSQ, and therefore, I may have this FET operating in the triode region, which is not the right region for keeping it in the active region. So, this keeps shifting. So, in order to obtain stable operating point, I should definitely clearly make IDSQ independent of the field effect transistor property, that is K or VT. How do I do it? Right. This is very simple. It is necessary, therefore, that this voltage VG should be shared between the FET and RS. So, I am introducing a resistance RS here. So, this voltage VG now, this is what we have got, VG, is going to be dropped between this and this. Is this clear? So, if I have this arrangement, now this is the equivalent. So, we get VG equal to VGSQ plus IDSQ RS. Is this clear? This voltage earlier was becoming totally equal to VGSQ, that was giving problem. So, what I did was put a resistance in series with the FET, so that the drop across the resistance is dominant compared to the drop across this. So, if this becomes now negligible compared to this, IDSQ becomes equal to how much? VG by RS, totally independent of what? The field effect device that you are putting here. So, if VGSQ is, if VGSQ is much less than IDSQ into RS. Is this point understood? What is VDSQ? VGSQ? VGSQ, strictly speaking, equals root of IDSQ by K, take square root, plus VT. From this equation, VGSQ is root of IDSQ by K plus VT. Now let me tell you, if you are designing a good FET, K is made very large, right? K is directly proportional to GM. Okay, GM is directly proportional to K. So if you want high value of GM, K should be high. That is number one. VT has to be made as small as possible. Okay, so that most of the FETs operate in the current saturation region, even at very low values of voltages, right, VDS. So VT is kept small, K is made large. That means this factor, okay, VGSQ, will be in most of the devices very close to VT itself, right. So you can use this information in sort of finding out the value of RS suitable for a certain value of operating current. This, when I take an example, you will understand it better. So this particular thing later has to be bypassed by using a capacitor CS. This also we had seen earlier, how to select the value of the bypass capacitor. Okay. It should be selected in such a manner that it is a short circuit compared to any impedance seen from it, okay, seen across it. So it should appear as a short circuit at the minimum frequency of interest of the amplifier. The reactance of this should be much less than impedance seen from this, or resistance across it. That part of it we will see later. Okay, what should be the resistance across this, etc. But now, if this is a short circuit, then it is very nearly equivalent to, as far as AC is concerned, this is, okay, going to be a short circuit here. Okay, in the equivalent circuit, this is a short, that is a short. Okay, so you get back your common source amplifier. This is only a biasing arrangement in order to bias it at a specific operating current. Now consider this example 11. Design a common source amplifier using N MOSFET with VT equal to 1 volt and K equal to 1 milliampere per volt square to operate at IDSQ equal to 1 milliampere and VDGQ equal to 10 volts. VDD is given as equal to 20 volts. Determine its voltage gain. So this is the problem. So let us see how we can go about designing this in a fairly simple manner without much of a difficulty. We know that we are going to use this VDD of 20 volts in order to derive whatever VGSQ that is required for this. It is required to operate this at a current of 1 milliampere, okay, and K is 1 milliampere per volt square. Okay. So VGSQ equals root of IDSQ by K plus VT. IDSQ is required to be made equal to 1 milliampere. So this is 1 by 1, which is 1, okay, plus VT equal to 1 volt. So this should be equal to 2 volts. And we are required to have VDGQ equal to 10 volts. So let us indicate it here. This should be 10 volts. This should be 2 volts. So essentially VDSQ VDSQ, okay, Q is VDGQ plus VGSQ, which is 12 volts. So actually we have exhausted 12 volts already in this, from here to here. Out of 20 volts. So you have only 8 volts left for a drop across RD and a drop across RS, okay, which is going to be 1 milliampere into RD plus RS. So if your intention is to make RS high, right, you have to make RD low. Please remember this. Right? So that is, you cannot therefore make RS as high as you please. Okay? There is a restriction on this. Further, we have this VG now, okay, VG equal to this 2 volts plus 1 milliampere into RS. This is VG. Okay. This is already given as 10 volts. Okay. So above this VG, we must have further 10 volts. Rest of it only has to be given to RD. Okay. Now, why I am emphasizing on RD is, RD should be made pretty large, strictly speaking, in order to make the voltage gain, which is GM into RD into RDS divided by RD plus RDS. Right. So if our voltage gain has to be made very large, we have to have RD as large as possible, okay, compatible with this idea. So however, this is already given as 2 volts. Okay. In order to make this drop, okay, negligible, this drop here negligible compared to the drop across this, then only it is a good, okay, operating thing. So I had to make RS as large as possible for this. For example, let us say, suppose VG is made 10 volts. This is 2 volts and this will be 8 volts. This is fairly good, okay, situation. This is 2 volts, compared to 2 volts, I have chosen 8 volts. But you might say, why 10 volts? If this is 2 volts, I would like to have here, okay, say 10 volts or even 12 volts or 20 volts. Is it possible? It is not possible, because compared to 2 volts, if you want to make this very high, strictly speaking, you should have chosen it as 20 volts. If this is 2 volts and this is 20 volts, okay, this is 22 volts. You have only 20 volts, right? So this is a problem. So here, for this given problem, I cannot make the operating point very stable. Do you understand this situation? I can make the operating point very stable only now if I make this very high. Suppose I am given liberty to select the voltage here such that I can make the operating point stable, then what would I do? For 2 volts, I will straight away take this drop as 20 volts. Okay? So this resistance will be straight away fixed at 20 kilo ohms, right, because 1 milliampere is flowing through it. So this is straight away 20 to 22 and then 10 volts here. Okay? So you have 32 volts. Okay? And then RD whatever you want. Okay? So that RD into 1 milliampere will be the supply voltage here. So I can select that supply voltage. Okay. So here the supply voltage is restricted, therefore you cannot make this operating point very stable. However, let us take this as now 4 volts, okay, or 8 volts. If you take it as 8 volts, straight away this will be 10 volts, this is 20 volts, no drop here. That means you cannot have RD at all, right. So we will take it as, let us say, 6 volts. So if this is 6 volts, then Rs is 6K, 1 milliampere flowing through it. So Vg is going to be 8 volts. This is already what? 6 volts plus 2 volts plus 10 volts, that is 18 volts. So what is required for Rd is 20 minus 18, 2 volts. So Rd is automatically fixed as 2 kilo ohms. So Rd is going to be, okay, 20 minus 10 plus 2 plus 6. This is that divided by 1 milliampere, which is, how much is it? 2K. Another design would have been, if I had chosen this as 4K, right, I could have had this as again 4K. You understood? What is therefore now fixed is 20 minus 12, 8 volts drop is fixed, okay, and current is 1 milliampere. So 8K, Rd plus Rs cannot be greater than 8K. It is just 8K. It is fixed at 8K. So if I select Rs as, okay, 6K, this has to be 2K. If this Rs is chosen as 4K, this will be 4K. If this is chosen as 2K, this can be 6K. So let us therefore leave it at this 2K. And what else has to be done? We have to fix up R1 and R2. So how do you fix up R1 and R2? R1 by R1 plus R2 times 20 volts should be equal to 2 plus 6, 8 volts. So R1 by R1 plus R2, that ratio is fixed now as 8 by 20 or 4 by 10. One way is, if I select R1 as 4 mega ohm, okay, R2 is going to be 6 mega ohms. So the design is complete, except that now I have to find out the gain. So how do we fix the GM? Is nothing but 2K into VGSQ minus VT, right. So this is 2 into K is 1, VGSQ is 2, VT is 1. So this is equal to 2 millisiemens. At the operating point, the GM of the FET is 2 millisiemens. Therefore, the gain is, right, RDS is not given. So RDS, when it is not given, we will assume it as infinity, right. It is not given. So gain, voltage gain is equal to minus GM into RD, which is minus 2 into 2 minus 4. It's a pretty low voltage gain. I had warned you that GM of a comparable dimension bipolar junction transistor will be of the order of 40 millisiemens or so at 1 milliamperes. Okay. So whereas GM of this is only 2 millisiemens, and therefore correspondingly the gain is pretty low. So it is very rarely therefore used as what? Amplifier. field effect transistors are not so popularly used as amplifiers compared to bipolar junction transistors for this reason, that the gain of the stage is pretty low. So, this example illustrates the problem of a field effect transistor amplifier design. What should be highlighted here is that this drop, okay, normally should be small compared to this drop if you want the operating point to be independent of the FET characteristic. So, let us say if you were asked to select VDD properly, so that is the case, okay, then if for a 2 volt drop you would take a 20 volt drop here. Yes. So, 20 volt drop, 2 volts drop, this would be 22 volts, okay, and substantial gain for the field effect transistor. So, you can select RD as a high resistance compared to this. So, if you have taken RS itself as, let us say 20 kilo ohm, right, we would definitely select this also of the order of, let us say 20 kilo ohm, let us say, right. So, 20 kilo ohm means further 20 volts drop. So, 20 plus 12, okay, 40, 52. So, VDD would have been 52. The cost of making the operating point independent of field effect transistor is that the supply voltage VDD will be of the order of, okay, 52 in this case. So, this kind of design, okay, you must always remember, if you are given the choice of selecting supply voltage etc. for these amplifiers. Another way that we had also discussed in the case of bipolar junction transistor is to use dual supplies. This is using single supply. How to use dual supply and bias the field effect transistor? That is pretty simple. So, we have this FET. Instead of using single supply, I will ground this and now use here, okay, this is VDD. I will use VSS here and put an RS here. This is the alternate way of biasing, okay. In the case of bipolar junction transistor, we started with dual supply and went over to single supply. In this case, we have started with single supply and going over to dual supply, just to make you understand the basic concept, okay, properly. If you are given the choice of biasing this using dual supply, then you will fix the current using RS itself here. So, it is very simple. Now, for the same problem, okay, this should be 2 volts, we are told, okay. Now, I have the choice of RS as well as VSS in order to make it, okay, whatever current I want. So, obviously, now I will select this straight away as 20 volts. Let us say 2 volts is very small compared to 20 volts. So, VSS becomes automatically equal to minus 22 volts. Is this clear? So, what is the value of RS? 20 kilo ohms. That fixes up the current independent of this VDG. VDG, right, is going to be 10 volts. So, now RD is going to be selected as 10K in order to make VDD equal to 20 volts. So, VDD is equal to 20 volts, okay. RD is equal to 10K because this 10 volts is already given to this, the other 10 volts can be given to RD, so that this VDD, okay, becomes equal to 20 volts. For the same problem now, the design is changed based on option to use 2 power supplies. The gain now becomes minus 20 because GM remains the same, IDSQ is the same. So, GM remains the same. So, since RD has been permitted to be selected as 10K, the gain is minus 20. The operating point is the same as the previous case, but I am now permitted to use, okay, 2 power supplies. The number of resistors that I need to use get cut drastically, and therefore, if you are permitted to use 2 supplies, straight away the resistors, okay, R1 and R2 are totally unnecessary.